2D planar manipulator. Okay, this is a problem we've done before. So we can always go back and check this against our math. In fact, this one you can also get the answer using simple trig. L1, L2, theta 1, theta 2, okay, those are pin joints, and this is the end effector. Okay. And the typical problem is compute the position and orientation of the end effector. Okay, now that's can be easily done using trig, but we'll use DH, and then if you want, you can go back and check your calculation. So what we're doing here is, I'm going to start with the algorithm from the handout. Step number 1, we'll assign a coordinate frame, and then we'll just keep going. So step number 1. Assign coordinate frames. Okay, so the first step, I'm looking at the handout, step number 1A, okay, which is also here. So I'll basically do A, then B, then C, and then D. Okay, that's what I'm doing here. Okay, so first step, assign Zi along the axis of actuation of each link. Okay, so the axis of actuation is nothing but the axis along which the revolute joint moves. So here the axes are going to be the axis through this, but that comes out of the plane of the paper. So instead of not showing it, let me just show it with a arrow like this. So this is going to be Z0, right? It's coming out of the plane, but I'm having a hard time drawing it like that. So I'll just draw it like that, but it's comes out of the plane of the paper. So that's Z0, and I need to keep doing that for all links. So I'll do it for this one. Yeah, and there are just 2 joints, so that will be 2 of them, Z0 and Z. Okay, the next step, number B, assign the base frame OOXO YO Z0. The Z0 has already been assigned, like I've shown here. Assign X0 arbitrarily and assign Y0 based on X0 and Z0. So what's saying is we need to assign Y0, and that Y0 can be assigned arbitrarily. Here I actually drew it, but this is easier to assign it this way because we are accustomed to X-axis being horizontal. So, but it's absolutely fine if you want to assign X0 along the, which I've shown as Y-axis, it's absolutely fine. It won't change anything. And then finally, you assign the Y-axis based on the right-hand rule. So what you need to do here is, so X cross Y should give Z. So if I curl my fingers from X to Y, that is at the right hand, then the Z gives me the thumb gives me the Z direction, that's what it is. So if I have Y there, it should all work. Okay, so that's step number B. Let's go to 1C. Okay. 1C. So there are 3 cases we need to check for. Now this is basically where I would say the hardest part of this whole thing, which is how do you assign Xi from I equals how to assign xi, where I goes from 0. We have already assigned x0, so x1, x2, and so on. Okay? We need to reason out about z, I, and I minus 1, and I. And depending on which case it falls, we need to choose one of those three cases. Okay, so let's first look at this. First, we'll look at, so we're always looking at a relation between zi minus 1 and zi. So here we're looking at a relation between z0 and z1, where I is equal to 1, right? And so once we've noted that how z0 and z1 are, let's go back to the handout, and ask ourselves, are z0 and z1 are not coplanar? Are they parallel, or they intersect? So in this case, they are actually parallel. They're coming out of plane of the paper. So it falls under this case. So then we go and read this. So there are infinitely many perpendiculars, right? If two things are parallel, there can be infinitely many lines between them. So it says choose any of these perpendiculars. Okay. There's actually a trick here. If to make equation simpler, choose xi such that it passes through OI minus 1. Okay, so what it's saying is, for this particular manipulator, since there are infinitely many lines, it says just choose it so that it passes through OI minus 1 or O0. So we go back. So this is one perpendicular. There'll be another perpendicular like this. There's another one like this. Say all of them like come, and they also will be more, right? So out of all these various perpendiculars, you're better off choosing the one which passes through OI minus 1. OI minus 1 is O0. So all it says is choose this to be your x0, sorry, x1. So okay, so we're done with that. Next, we look at the next two sets. So I assumed I equals 0. Now let's take I equals 1. So I need to look at the relation between z1 and z2. So if you go back here, we see there's no z2, right? You not assign z2. So that's where we stop. We don't need to go any further. Okay, next step is, so we've assigned xi. We also need to, if you want, you can assign yi. It doesn't really affect the dh, but some people want yi. So if you want to assign yi, then just use the same fact that x cross y should be z. So if you have x along this, z along here, I should actually use a red color. So here's this. These are x1. So the only way we can achieve the right-hand rule is to have y1 this way, so that when you curl your finger from x to y, your thumb gives the direction of z1. Okay, so here in this case, we are done with the first three steps. Last step is we need to attach end-effector frame. That's the last thing. In this case, n equals 2. Attach zn to be the same direction as zn minus 1. Okay, and depending on the relation between zn and zn minus 1, attach frame extends. Let's just break it down. Let's attach zn to be same direction as zn minus 1. So here n equals 2. So we need to look at relation between z2 and z3. Back. So same direction as z1. This will be z2. The same direction as z1. And then we need to see the relation between z1 and z2. So I think I wrote it incorrectly here. So relation between z1 and z2. So if you look at Z1 and Z2, you see that they are parallel to each other, just like Z0 and Z1 was. And so you again go back to these cases. These cases and figure out what it falls under. So here it falls under number 2, C2, Zi minus 1 and Zi are parallel, or Z1 and Z2 are parallel, in which case you need to draw there are infinitely many perpendiculars, and you choose the one which passes through OI minus 1 or O1. So go back here. This is O1. And we choose X2 to be this way. And then as I said, you don't have to put white if you want. You can put it, but it really doesn't affect our the DH table later on. So step 2. Okay, the DH table looks like this. I've already put a copy there. Link AI, alpha I, TI, theta I. Okay, so here we have two links. So I need to populate those A's and A, alpha, D, and theta. Okay, now let's go to step 2. Okay, so what I feel is you can do it one of the two ways. There may be more ways. You basically need to use this figure to figure out the relation between generate that table. Basically depends on how Zi and Zi minus 1 is related to Zi and how Xi is related to Xi minus 1. I've developed my own technique which helps me, and maybe I can convince you that it's easier than that figure. So what I do is I draw two figures, which actually is in the handout. Put all this in one. Okay, so here are my two figures, which help me to get this table. Yeah, so AI, alpha I will come from here, TI, theta I will come from here. Okay, so let's start with first link. Okay, to get AI, it is nothing but the distance between, well, let's say the angle first. It might be easier than the distance. So alpha I is the angle between Zi minus 1 and Zi when rotated about the Xi axis. Okay, so what is I first of all? I is 1. And so we are trying to figure out the angle between Z1 and Z0 about X0. Okay, and then when you are doing this, you need to go from Z0 to Z1. So maybe I should write it this way. So angle from Z0 to Z1 along x1. So z0 is here, z1 is here, okay? And I need to rotate about the x1 axis, which is this, and find the angle between z0, 0, 1. But when I look at it from x1, so maybe it's easier for you to think of it this way. Z0 is pointing out, Z0 is pointing out, Z1 is pointing out. And then we're trying to see what is the angle between these two about this axis. So they are parallel to each other, right? And so the axis between the two has to be 0. Let me show. So we're going to view this way. This Z1 and Z0 are parallel, or the angle between them is 0. So this becomes 0. Okay, this requires a little bit, I guess, practice. So the more you do it, you get the hang of it. Okay, next is the AI, which is the distance between Z0 and Z1 along X1. So distance between Z0, Z1 along X1. So along this axis, we need to compute the distance between these Z0 and Z1. So you can see that it's L1. So that would be L1. Okay, next, we are here. We need to compute, let's do the angle, which is easier. Theta1 is the angle between, let's put I equals 1. So x0, x1. So I equals 1. So x0, x1 about z0. So the angle between x0 and x1 about z0. So x0 is here, x1 is here, and we need to find the angle about z0. So about the axis like this. This is x0, this is x1. The angle about z0 would be theta1. Right? The angle between z0, x0 and x1 about this axis is theta1. And then the distance between x0 and x1 about z0. The distance between x0 and x1 about z0. So when you look at it this way, if you see that x0 and x1 are offset, then they will have a non-zero distance. But here they are in the same plane. At the same, they are both in the xy plane. So when you look at it from here, the distance between x0 and x1 is basically 0. So 0 there. Okay, and the good thing about this manipulator is that whatever I just described, same thing, same rationale will go when you put I equals 2. You'll basically do so Z1, Z2 about X2, and then X1, X2 about Z1. Because it's essentially the same reasoning because Z1 and Z2 have the same relation as Z0 and Z1. So really, it's the same thing. It would be repetition. So what you'll end up with is L2, 0, 0, theta 2. Okay, there's nothing new here. So I'm not really going through this. So that is our DH table, which is, these two steps are the hardest ones. The final step is to use the DH transformation. So we have H1 with respect to 0. I'm going to write a shorthand notation and then put what it means. L1, C1, L1, S1. The C1 is cosine theta 1. Okay, so where did it come from? Well, it came from that H. I only needed the parameters A1, D1, theta 1, and alpha 1. Right? Once I have these values, I can compute this. And similarly, C2 minus S2, S2, C2, 0, 0. Zero. So C2 is cosine theta 2, S2 is sine theta 2. Okay, that's the two homogeneous matrices associated with the two links. And then finally, H20 is H10, H21. When you do the math, it comes out to be C12, S12, minus S12, C12, 0, 0, L1, C1 plus L2, C12, L1, S1 plus L2, S12. This comes from A2, T2, theta 2, alpha 2. And then C12 is cosine theta 1 plus theta 2. S12 is sine theta 1 plus theta 2. Yes, as I said, if you want to compute our goal here is to compute the end effector position and orientation. This is the orientation of end effector. Okay. It's a matrix, right? But you can see that it's theta 1 plus theta 2. That's the angle made by the end effector with, in this case, z-axis. And then this is the position. Of end effector, which is exactly what we got earlier, L1 cosine theta plus L2 cosine theta 1 plus theta 2. Okay, here's example 2, and maybe I will not be able to finish it today. Number 2. There were 3 link manipulator, and now I'm going to show you a very weird way of drawing the manipulators, but that's how we'll be using it, because we are really not interested in how the manipulator looks. All we care about is that where the joint is and what is the degree of freedom. So this is how I'll draw the manipulator. It's a 3D manipulator. And just to remove clutter, I'm just going to show a cylinder for the revolute joint, and I'll be showing an axis. So that's a revolute joint, and the axis is oriented in the direction shown. Okay, then this manipulator has a prismatic joint, and I'll use a cube. So that direction shows the way this prismatic joint moves up and down. Okay, and finally, I'll have another prismatic joint. Okay, and that's my end effector. Okay, so remember that I've not joined a link. I've only drawn joints. The link, there's like a link here. And there's a link like this, and so on, right? Those are not shown. This and this are joints. Okay, and then I need to show the distance between these two, L1. Links are not shown. Okay, now this particular manipulator has one revolute joint and two prismatic joint, and you'll see a terminology like this, 1R, 2P, meaning this is one revolute, two prismatic. Okay, so you often see 1R, 2P, which says 1R, 2P, it means it's one revolute, two prismatic, and then you can use that logic to think of other manipulators. So the question is same as before. Find the position and orientation of the end effector. Okay, let's assign coordinate frames. Step number 1. Okay, so reading from the handout, we have step number 1 is assign Zi along the axis of actuation. So let's see. So the axis of actuation is this. This is going to be my Z0. The axis of actuation of this one is this. So Z1. And the axis of actuation of the last joint is this. So let's just put it here. Z2. Okay, that's step number 1. Next is assign the base frame. So the base frame, the convention is you can assign X0 whichever way you want. It doesn't really matter. Just ensure that it is right angles, right? So here I chose to assign it in this fashion, X0, but anywhere is fine. You could do it anywhere in this plane. Okay, and then the final one is y, that would be right angles to x0 and z0 such that it follows the right hand rule. Okay, I'm done with, so 1a is done, 1b is done. Next page, 1c. Okay. So I'm doing 1c now. In 1c, I need to assign the axis x1 and x2. That's all. In order to assign axis x1, I need to understand what is the relation between z0 and z1. And so there are three cases. I can tell you that number one case, not coplanar, doesn't really apply to any of the problems we're doing. It's only usually 2 or 3. Okay. Now it says zi minus 1 and zi are parallel, and zi minus 1 and zi are intersecting. Which of those two do you think it's true? First one is parallel. So when you say parallel, it comes in pairs. So we need to understand what is the relation between z1 and z0. It's you said so first one, I mean z0 and z1, you said parallel. So parallel is fine. Intersecting is also true for this one. You could use either one. So let's assume it's parallel. If they're parallel, then you need to assign, there are infinitely many perpendiculars. We draw xi. So where xi intersects. So if they're parallel, there are infinitely many. Perpendiculars. Okay. And I think I'm just having a hard time figuring out the perpendicular. So why don't I just go with the second case, which is the intersecting? That looks more appropriate, because then I have to find, I don't really see a way of drawing perpendiculars to them because they are sort of in the same line. So let's go with the intersecting one. It seems more appropriate here. So if they are intersecting, then you draw the, so it says, so this is C for link Z0, Z1. We have intersecting. So when it's intersecting, then xi is chosen to be normal to the plane formed by zi minus 1 and zi. So we need to choose an axis which is right angles to z0 and z1. Now, when I say right angles, there are infinitely many right angle directions. So this is a plane which is right angles to the axis, and you can choose any xi. Xi could be in any direction. Right? It's up to you. So what I did was I chose this direction. Okay, which is very arbitrary. It doesn't have to be this. As I said, it can be any direction, but in this plane. It's perpendicular to z0 and z1. Okay, now we got x1. Last, we need to get x2. So for that, we see the relation between z1 and z2. Again, we see that z1 intersects z2. So the axis for x2 would be right angles to z1 and z2. So now we have only two choices, as I'll show. We have, so this is z1, right? So one choice is this way. Another choice is this way. So we can have either x2 this way, or we can have x2 that way. Just two choices. And you can choose either of those choices. Both choices are valid choices. So that's, I just chose in my notes, I just chose x2 to be this way. Let me stick with that. So here, P1, Z2 is intersecting. That's why I chose what I chose. Okay, so we're done with number C. Let's go to number D. Okay, the number D says, how do we choose the coordinates for the end effector? what we need to do is we need to assign the z-axis for the end effector to be the same direction as that for the previous link. So in this case, you would put z3 in the same direction as z2, and then x2, and then of course if z2 and z3 are that way, then we need to assign the x3 based on the relation between z2 and z3. Here z2 and z3 are intersecting, which means we need to draw x3 right angles to z2, z3. You can choose any normal in this plane. Anything will work, right? Because there are infinitely many, because it's a plane and there can be infinitely many perpendiculars. I just decided to go with something which is parallel to x2, just makes my life easy. And that's pretty much it. We've done with what D is done. Okay. Now you can go ahead and assign y1 and so on. So x cross y should be z, so it has to be that y. Okay, over time, I'll stop off with this. Y1 and x cross y. So y should be downwards. And then x cross y z. Okay, so we've assigned the coordinate frames. Next time we'll continue this and assign, generate the DH table. I'll just do it one line of the DH table at a time. So I'll first figure out the A, D, alpha, and theta for the first line of the DH table. Okay, so for that, what I need is, so my goal is to compute AI, alpha I, DI, theta. Okay, so let's start with A and alpha. What's the definition of A and alpha? It is in here. Okay, let me see if I have it. Okay, so this is how you get it, but this is how I do it. Instead of using this, in your handout, there's a way in which I do it, and it is pretty much page. So page 3. Okay, so I'm going to use this sort of cheat sheet to do it, and I'll show you how I do it. Okay. So for AI alpha I like to draw this figure. So since I is, okay, I equals 1, alpha is 1. I simply put I equals 1, so I have z0, z1, x1. Okay, and so the convention is that alpha 1 is the angle between z0 and z1 about the axis x1. So let's see that in this figure. We've already drawn z0. Z0 is here, like this. Z1 is also up, so let's draw that. X1 is this, so X1 is pointing this way. Okay, so what I need to figure out is what's the angle between Z0 and Z1 about the x-axis, or X1 axis. Okay, so you can see that Z0 and Z1 are actually in the same line, which means that the angle between them is 0. And so alpha 1 is 0. Okay. To get A1 is the distance between Z0 and Z1 along X1. So when you look at it from here, you can see that Z0 and Z1 in the same line. So the distance between these two axes, Z0 and Z1, along this direction is simply 0, right? If it was not 0, then you'll have Z1 will be offset. If this is offset, then this is a non-zero distance. But since it's in the same line, A1 should be 0. Okay, next, let's do the second link. Sorry, the first link, but D1 and theta1. Okay, so again, if you look at page 3, the way I like to think of this is in that figure, I have drawn x I minus 1. So I is 1, so x0, x1, and then zi minus 1. So zi minus 1 is z0. And so theta I or theta1 is the distance, is the angle between x0, x1 about the z0 axis. So we'll do the same thing, which is we have x0, just drawing x0 the way it is here. We have x1, okay? And then z0 is this. So z0 is right angles. Okay, now to figure out what theta1 is, it's basically the angle between x1 and x0 about z0. So if you see x0 and x1, you see that it is in the same line. So the angle is in this configuration is 0. But remember that the manipulator has theta1 as a degree of freedom, which means that at any given instant of time, theta may not be 0. It will actually be some angle. So when theta1 is rotating, x0 will keep rotating, right? It will be here, then it will be here, and so on. So what's happening is this angle is changing. In fact, that's what the manipulator is for, right? It's basically going to move that joint. So the angle is not 0. It's 0 in that particular configuration, but for a generic theta1, it is not 0. It's in fact theta1. So theta1. Okay. Hold on. I think I might have. Let's look at this way. X0. This is positive theta. Okay, so I think I might have made an error on the sign. So we need to rotate the vector x0 to go from x0 to x1. So we need to go from x0 to x1. And the angle swept is actually negative, right? Because you always go from, at least the sign shows. So if you can see this, this is how I've shown my convention. Theta1, it goes from x0 to x1, but this arrow is in the direction opposite to that arrow. So it has to be negative theta1, my bad. So this actually, if I had shown it the other way, theta1 to be the other way, then it could have been positive. So if this is shown in the direction it's over here, this would be negative theta1 with the correction. And the fourth parameter is the distance d1. This is the distance between x0 and x1 along z0. So that is distance between this axis and this axis about z0 axis. So you can see that that distance is nothing but L1. So d1 is L1. Okay, in other words, the distance, if you see it from here, you need to measure the distance along the z0 axis, and it's the distance between x0 and x1. Okay, so that's the first line of the DH table. Okay, we just keep doing that for the second and the last end effector link. Let's do that for link 2. So A2, alpha 2, T2, theta 2. Okay, so I'm going to do the same figure I drew earlier. This is from page 3. We have I equals 2. So we have the angle between Z2, that is Z1, and Z2 about axis X2. This will be alpha 2. Okay, so based on this, let's redraw axis Z1, Z2 from this figure. Z1 is pointing upwards. You can see here. Z2 is pointing to the right. And X2 is pointing, coming out of the plane of the paper. So it's this way. Okay, so let's figure out what alpha 2 is. So it's the angle between Z1 and Z2 about X2. So let me just draw the Z1 expression. Z2, Z1. Okay, so following this convention, so the angle between Z1 and Z2. So I need to sweep from Z1 to Z2. So I need to go Z1 to Z2. So you can see that that sweep is 270 degrees. Okay, and note that when I'm sweeping this, so if I curl my fingers of the right hand from Z1 to Z2, my thumb should be along X2. Okay, that's why I went that way and I did not go the other way. I did not go this way because I need to go from Z. When I curl my fingers from Z1 to Z2, my thumb should give me the direction of X2. And similarly, the same thing was used here. Okay, so it's either 270. Now, if you want to go the other way, the shortest angle, then that angle would be minus 90, because in order to sweep from Z1 to Z2, I need to curl my finger, my thumb will be pointing in the other direction. So either you can write this as 270 or minus 90, both are valid. They'll give you the same answers if you put either of those two. Okay, next we need to figure out A2. A2 is the distance between Z1, angle between the distance between Z1 and Z2 about X2. Okay, so we've already drawn C1. In fact, it was here in the figure, Z1 is this way, Z2 is that way. So you can see that Z1 and Z2 actually intersect. So Z1, Z2 intersect. And we're trying to figure out the distance between those two about X2 axis. Okay, so if you want to find the distance along the X2 axis, we need to look at it from the side this way, as along this axis. And we see that Z1 and Z2 are in one plane. You can see here, Z1 and Z2 are in the same plane. And so if they're in the same plane, then the distance along this axis has to be 0. Okay, the other way would be if Z1 was this way, Z2 was like this, and then this was X2, then this distance is non-zero. because now in this situation, which is not the same one which I have over here, the distance is not 0, because when you see the two axes along x2 direction, you see that the distance is finite, this distance. Yes, but that's not the case. So write it down. This should be 0. Okay, I think I swapped the colors. Use blue for this. Okay, next let's figure out the same things, so D2 and theta2 for link 2. So for that, I'll use the figure from page 3. I put I equals 2, and I would have Z2, Z1, Z2, X2. Alpha 2. So alpha 2 is the angle between Z1 and Z2 about the X2 axis. This is positive. Okay, so let's draw Z1 and Z2. So Z1 is pointing upwards, Z2 is pointing to the right. And then I need to measure the distance and the angle about X2. Nothing wrong. Wait. My bad. So this is my bad. This is not for, this is for alpha. I need for theta. Copied it wrong. So this should be between x1, x2, about z, I minus 1, so 1. So angle between x1, x2, about z1. That's the right one. So I need axis x1. X1 is coming out of the plane of the paper. X2 is coming out of the plane of the paper. X1, X2, and then Z1 is right here. Z1 is up. Okay. So first is the angle theta 1. Theta 1 is the angle between X1 and X2 about the Z1 axis. You can see that X1, X2 are actually in line. They're in the same plane. Right? This plane. So if they're in the same plane and they are collinear, then the angle between those two is going to be 0 as viewed from the z-axis. So that should be 0 for theta 2. And then the final thing is G2, which is the distance between X1 and X2 about the Z1 axis. So when you look at it from the side along Z1, what is this distance? It's pretty much D2, I think. It's D2. So this would be D2. Yeah. It's a prismatic joint here. Say that again. The distance will change. That's why it's written as D2. And you can put any value you want for D2. Okay, so that's the second line of the DH table. Last one is link 3. Let's do that for link 3. Okay, so we want A3, alpha 3, P3, theta 3. Okay, so let's again use this convention I've used to figure this out. So let me draw what alpha I is or alpha 3 is. It's basically the angle between Z I minus 1, I is 3, so Z2, and Z3, about x3. Okay, so I'm going to draw z2 axis, z3 axis, and then figure out the angle about x3. So z2 is, you can see, is to the right. z3 is also to the right. And x3 is pointing out of the plane of the paper. So z2, z3, x3. Okay, so that should be enough to compute alpha 3. So z2 and z3 are collinear, and so the angle made between those two about x3 axis is going to be 0. Alpha 3 is 0. A3 is the distance between z2 and z3 about the x3 axis. You can see if you look at it from here, you see that this is in the same line. So the distance along x3 is going to be 0. Okay, so that was fairly straightforward. Let's do d3 and theta 3 now. Okay, so I'm going to draw the other figure I have to compute or figure out theta 3 and d3. So I equals 3, so x2, x3 about z2. So this will be theta 3. Okay, so let's draw x2 and x3. x2 is pointing out of the plane of the paper. x3 the same thing. And z2 is to the right. So x2, x3, and then z2 is to the right. Okay, so now in order to compute theta 3, it's going to be the angle between x2 and x3 about z-axis. So when you look at it from this way, you see that x2 and x3 are in the same, are collinear. Right? You see them, they're exactly on top of each other when you look at it through z2. So the angle between x2 and x3 is going to be 0. And then you need to compute the distance between x2 and x3 about z2. So about this axis, you want the distance between x2 and x3, which is this distance. And that distance is nothing but d3. d3. So d3. Okay, that completes the last line of the DH table. So I just put it all together in one place. Okay, so the DH table is as follows. Link AI, alpha I, Ti, theta I. We have 1, 2, 3. Can you just copy pasting from previous pages? 0, 0, L1, theta 1, the minus sign, 0. And this one I said it could be 270 or minus 90, both are fine. D2, 0, 0, 0, D3, 0. Okay, so then I can compute hi minus 1. This is straight from the handout. It's a formula which I will not write, but you can write a 4x4 matrix, which you'll probably do using SymPy. So CH handout. Okay, so this will give you the following things. It will give you H01, H12, H23. Since there are 3 lines, there will be 3 H matrices, which will correspond to I equals 0, Okay. My bad. This should be the other way around. And this should be 0 up and 1 down. So the upper index is lower. 2, 2, 1, and then 3, 2. So I equals 0, 1. Sorry, I equals 1, 2, and 3. That was what was used to compute H's. And once you have all that, you can compute 0, 3 is H. H3, 0. The H1, 0, H2, 1, H3, 2. And when you do this multiplication based on the H you get by putting in I equals 1 to 3, you will have a matrix which looks like this. So DR3, 0, D3, 0, 0, 1. This part gives you the orientation of end-effector. And this part gives you the position of the end-effector. Okay, and obviously I will not do it by hand. I'll just use symbolic computations. And then the question, like always, we find the position and orientation of the end-effector. Okay, so you might recognize that this part, if you ignore the first link, ignore this one, this part is something we've already done before. It's basically the planar manipulator we've talked about. The only thing we've done here we added this link with this joint, which means that now it's a 3-dimensional manipulator because this axis θ1 is in a different plane compared to θ2 and θ3. So it's a little bit more complicated, but it's a very slight extension of what we've done so far. Okay, so let me go to step 1, which is figuring out the coordinate frames. So let me copy this. Okay, all set. Okay, let's follow this steps. Number 1. So first, step number 1A, assign Zi along the axis of actuation for each link. So let me use blue for the Z axis. So clearly this is Z0, this is Z1, this is Z2. These are 3 links, 3 joints, 3 Z's. Okay, next, let's assign the frame X0, Y0. So this is the base frame. So I'm on 1B. Assign the base frame OO, XO, YO, ZO. The Z0 has already been assigned, as you can see. Assign X0 arbitrary. So we have a choice to assign X0 arbitrarily. Now, the only thing you want to do is you don't want to assign X0 along Z0, right? So you want to assign X0 in any plane which is right angles to Z0. That's all you need to be careful about. So I've drawn that, but let me erase that just to remove clutter. Okay, so what I did was I stuck with the axis this way. Okay, but this one is perfectly fine. This one is perfectly fine. Anything in 90 degrees is perfectly fine. Okay, and then if you want to complete it, this is not required. If you want to complete the coordinates, you can draw the y0 such that when you do x cross y, you should get z. So x cross y, when you curl your fingers, fingers were right from x to y, you get z pointing upwards, so it's the right convention. However, for dh, you don't really require the y-axis to be shown. Okay, so that's 1b. So 1a is done, 1b is done. Next, go to 1c. So 1c assigns x1, x2, and it's based on the relation between z's. So we need to see how the consecutive z's are related. So we have z0 and z1. So z0 is upwards, z1 is this way. And then we need to figure out which of these three it belongs to. Zi minus 1 and Zi are not coplanar, Zi minus 1 and Zi are parallel, and Zi minus 1 and Zi are intersecting. So in this case, Zi, so Z1, this should have been Z0. So Z0 and Z1 are intersecting, and so it's C3. So if Z0 and Z1 are intersecting, xi is to be chosen normal to the plane formed by Z0 and Z1. So x1 is normal. So if Z0 is this way, Z1 is this way, okay, we have pretty much two choices for x0, sorry, x1. One of them is this way, another is this way. Okay, you can use either of them. There are only two choices. Okay, so I just decided to go with this way. Yeah, again, using the other way is fine too. It will give you the same answer. You get a different DH table though, but you'll get the same answer for the end effector. Okay, next is, again, we need to attach frame x2. So we see what's the relation between Z1 and Z2. So again, 1C. So we have, the first one is ruled out, not coplanar. Zi minus 1, Zi are parallel. So Z1 and Z2 are parallel. That's what it looks like, right? Z1 and Z2 are parallel. And so if they are parallel, then there are infinitely many perpendiculars. Choose any of these perpendiculars, right? So we can choose any perpendicular. Any of these could be x2. Okay, but if you want to make your life easy, then you want to choose x1 or x2 such that it passes through the origin of the previous joint. So that would be this joint. And so if you choose x2 to be this way, then it passes through the origin of the previous joint, makes it easier for the DH table. So that was number 2 for link 1, link 2, or link 0, or joint 0, and put joint 0, joint 1. Okay, so we are pretty much done with step C. Next, move to step D. So finally, we need to attach end effector, attach Zn to the same direction as Zn minus 1. So in this case, Zn is going to be, the next number after 2 is 3. So Z3 is going to be in the same direction as Zn minus 1, so Z2. So we'll attach Z3 in the same direction as Z2. And then we'll go back to this C and figure out what is the relation between Z2 and Z3. Z2 and Z3 are parallel to each other, which means that there are infinitely many perpendiculars. We choose the perpendicular which passes through the origin of the previous link. And so we need to put x3 in this. Okay, so that completes the coordinate frames, and now we can move on and compute the figure out the DH table. I'm going to copy this. Okay, so DH table link. One, two, three. Alpha I. Okay. And then the thing which I'm going to use is the same thing I drew on page 3. Zi minus 1, Ci, Xi. This is alpha I, Xi, Xi minus 1, Di minus 1, and this is for theta I, and theta I Di pairs, and alpha I Ai pairs. Okay. Okay, now let's do it without really drawing all those figures like we did in the previous problem. Okay, so I'm going to use just these 3 pieces. That's the figure on top with the frames. You can get rid of the clutter. We need this. Okay, we're going to use the figure on the right, these figures, and then just populate that table. Okay. Okay, let's start. So first I put I equals 1. And let's try to populate the first 2, AI or A1 and alpha 1. For that, we look at this figure. So alpha I is going to be the angle between Z0 and Z1 about the X1 axis. So Z0, Z1 about the X1 axis. So Z0 is here, Z1 is here about the X1 axis. So Z0 is up, Z1 is to the right, X1 is to the right. So it's the angle between Z0 and Z1 about the X1. So if you curl your fingers from the lower one, Z0 to Z1, so you go from Z0 to Z1. So you curl your fingers from Z0 to Z1, your thumb is in the direction of X1, so it's positive direction, and this is 90 degrees. So this should be 90. Okay. Okay, next is the distance between Z0 and Z1 about X1. So Z0 is like this, Z1 is like this, and we need its distance along X1. So you need to view it right angles to the axis. So if you're viewing it from here, this way, then you see that Z0 and Z1 intersect. And so the distance along X1 is going to be 0. So the second one, this one is going to be 0. So that completes the 2 of those. Let's move on to theta I di. Okay, so I put I equals 1. So x. So theta 1 is going to be the angle between x0 and x1 about z0. x0, x1 about z0. x0, x1 about z0. So let's just draw that. x0, x1, and z0 is just. Okay. So the angle between x0 and x1 about z-axis, you can see that x0 and x1 line up on top of each other. So the angle between them is going to be simply 0. My bad. It's not 0. It's, remember that it's rotating about theta 1, right? So at this instant of time, it is at 0 degrees. But when the manipulator has turned, or the joint 0, joint 1 has turned, it will be some value which is non-zero. So let's say it's theta 1. So this will be theta 1 and not 0. Okay, it's only 0 for that instant. So it's a parameter which can be tuned based on how you position the motor on joint 0. And then D1 is the distance between x0 and x1 about z0. So the distance between this line and this line about Z0, about this axis. So it's this, so it's going to be L1. Okay, that's the first line. We did a lot less work than we did before. Okay, now let's do the second line. So I need to put I equals 2. So X, let's do this one first. It's easier, alpha. So I equals 2. So the angle between Z1 and Z2 about X2. So Z1, Z2 about X2. Let's look here. Z1, Z2 about X2. Let's draw that. Z1, Z2 or X2. Okay. So to get alpha I or alpha 2, I need to compute the angle between Z1 and Z2 about this axis, but you can see that Z1 and Z2 line up on top of each other when you view it from here. So this angle alpha I should be 0. Okay. Next is the distance between Z1 and Z2 about X2. So distance between this vector and this vector about this axis. So it's going to be this distance. And that distance is given as L2. This is L2. Okay, so we're done with 2 numbers. Let's do the other one from this figure. So I equals 2. So X1, X2, Z1. X1, X2, Z1. X1 is here, X2 is here, about Z1. So let's draw that. X1, X2, about Z1. Okay, so we don't really need this figure now that we have drawn this. Now it's the angle between X1, X2 about Z1. So you can see that X1, X2 line on top of each other. So the angle is 0 in this particular configuration. However, when the manipulator rotates by angle theta, this X1 will actually rotate, it will go up. So the angle will not be 0, but will be some angle theta 2. So this will be theta 2. And then finally, the distance between X1 and X2 about Z1. So you need to view from here. So if you view from here, you see that X1, X2 in the same line, that the distance along Z1 is going to be 0. This will be a 0. Minus what? Theta 2. See. So okay, so for that we need angle between Z1. So X1 next, X1 is this way, X2 is there. When it rotates, different color. So let's try in rotated configurations. This is theta 2. So the angle between your right X1, between X1 and X2 about the axis V. Yeah, so you're right. It should be negative. At least the way I've drawn it here. Because in order to turn from X1 to X2, so if you need to curl your fingers from X1 to X2, then their thumb is in the direction of negative V1. So that should be a negative theta 2. Okay, and then I was just trying to make some space here. Enough space for the last one. Okay, finally, we are the last link. Now, here we need to again do AI alpha I. So I put I equals 3. So I'm looking at Z2, Z3 about X3. Z2, Z3 about X3. So Z2, Z3 about X3. So the angle between Z2 and Z3 about X3 is going to be 0. Next is the distance between Z2 and Z3 about X3. So it's going to be this distance, which you can see is L3. We're done with that. Next, we need to put I equals 3 here. So X, the angle between X2 and X3 about Z2. X2, X3 about Z2. X2, X3 about Z2. X2, X3 about Z3. No, Z2, sorry. I equals. Okay, so this is just this configuration, but when it X2 rotates, it's going to go rotate like this. It'll be theta 3. And so the angle is going to be just like the previous, will be negative theta 3. And then this is going to be the DI will be the distance between X2 and X3 about Z2, but they're in the same line. So when you view it from this side, this distance is 0. Okay, so that is my DH table. And then I can use this to compute H, just like previous case, and then compute the position of the end effector. Okay, so what we'll do is third step, H I minus 1 is a 4x4 matrix, which you can get from the DH handout. We'll compute H10, H21, H32. That's easy to get once you have a symbolic toolbox. H30 is H10, H21, H32, which will be R30. Okay, and then once you get this, this is the orientation. This is the position.